I'm going to hope that this is sufficient. And thank you, Franco, for that trip down memory lane. And as you know, our early careers were very parallel, and it's wonderful to be with you here. And so good morning from Vancouver, which is on the west coast of Canada. My hope had been to come to Kigali, but unfortunately that was not the case. But still, I really appreciate this opportunity to tell you a little bit about how I might think as an experimentalist who is motivated by looking for new materials, how these new materials might support the quantum computation, quantum information work that's the main topic of this conference. So the work I'm going to tell you about today is carried out at our laboratory, the Quantum Materials Discovery Lab, that was founded by myself and by Alana Hallis at the Stuart Blusson Quantum Matter Institute at UBC. These handsome people in this slide are our trainees, our students, and our postdocs who have been carrying out this work. To start, I could perhaps encapsulate the purpose of our work as searching and trying to understand the properties of a particular kind of system that is going to go by the name of a quantum spin liquid. This slide is meant to represent, what it is that we know and how we can use this information potentially to try to find real manifestations of this kind of a compound. So the quantum spin liquid that I want to talk about is manifestly magnetic. It has magnetic moments. What's important, though, is that these magnetic moments do not order. They don't break any symmetries in this system. And so in that respect, since the state can be found potentially at zero temperature, we view it as a new state of matter, analogous to the ordered phases that we're more familiar with. So as I said, the consequence of not breaking any kinds of symmetries, in particular translational symmetry, the magnetic moments themselves have the properties of a liquid and not of a solid. In the absence of magnetic order, you could ask, what's the alternative? And the answer is that magnetic order is ordinarily suppressed by arranging there to be, for one reason or another, very strong quantum fluctuations, which overwhelm the tendency to order. But you should not be confused that this material is a paramagnet. It definitely is not that. In a paramagnet, the magnetic moments fluctuate independently of each other, both with respect to position and to time. And in the case of a quantum spin liquid, those fluctuations are not wholly independent, and long-range interactions can lead to the entanglement of the magnetic wave functions. That's manifestly different to a paramagnet. So as an experimentalist, I find the following list both, motivating and disappointing. In the sense that the properties of a quantum spin liquid are poorly defined, but they are related to effects, as I say, such as quantum fluctuations, to the entanglement over long length scales and long time scales of the magnetic wave functions themselves, and potentially to their coherence. Finally, we know that the topological characters are very important for the functioning of these materials as well. So from my own perspective, you have to ask and answer the question every day, which is, how would you know a quantum spin liquid if you saw one? The properties from sort of simple experimental perspectives are still a little bit on the mysterious side, but we understand that they would include, following the properties of the wave functions, that the excitations should be non-local and potentially topological. But as well, the excitations themselves will be unlike ones that you have seen before, in the sense that they are not simple excitations of electrons or conventional magnetic moments, but there is the possibility that the excitations are built out of parts of those familiar excitations. So maybe the charge, but not the spin, or the spin and not the charge. So those excitations are thought to be fractionalized. So with that introduction, I want to launch into talking about the general constraints that we have in terms of finding these new materials. So the first thing, of course, to point out is that I'm talking about magnetic systems. And so, although it may sound sort of trivial to say it, we want to make sure that the materials we're looking at have magnetic character. But the problem is we don't want too much character. If we have too much magnetism, then we will always get magnetic order, and that's not what we want. So the periodic chart, of course, is always our inspiration. And so, of course, you know that magnetism is related to partially filled D and F shells in materials, in elements. And so since many neutral atoms in the gas phase would have partially filled shells, inherently, magnetism is everywhere in the periodic chart. However, what we know is that as we bring together the atoms to form an extended solid, the magnetic character can be strongly modified by that hybridization. And so if you look, for instance, on the left-hand side of a row, so say over here, what you find is that the hybridization is what you find is that the d orbitals in this range of elements, for instance, are highly delocalized, and so they don't bear a magnetic moment, and we see non-magnetic metals. On the other hand, if we go to the right-hand side of the row, this is the consequence of a progressive shrinking of the D and F electron wave functions that we localize them, and they can bear a magnetic moment. And so the further to the right that you go on the row to first order, you can say the stronger that the magnetism is. So where we want to be is somewhere in between those two limits. And for instance, in the 3Ds, chromium, manganese, and iron have depending on their chemical environment, can be either magnetic or non-magnetic. And similarly, we can say the same for F electrons. And so this is our happy hunting ground, where we look for materials that are magnetic, but not too magnetic. So say we find, so we limit ourselves to systems that we think are potentially magnetic, and you have to ask yourself then, okay, how do you ensure that there's not magnetic order, but potentially that we'd like to be near magnetic order. So here I think, we can say that there is really significant amount of progress that's been made. And as evidence, I would give you these 4 different phase diagrams that are represented here. So let's start with this one, cerium palladium 2 silicon 2. It's what's called a heavy fermion compound. It's an antiferromagnet, but as you apply pressure, you see that the nail temperature drops. And just where antiferromagnetic order is going to disappear at what we call the quantum critical point, the 0 temperature antiferromagnetic transition, we see this little bubble of superconductivity emerge. Something very similar can be found in, say, the cuprates, the organic conductors, the iron pnictides. And despite the fact that the microscopic physics of these systems is very different system by system, we can see that this quantum critical point is a critical part of these correlated electron systems. So you could say, well, the simplest way to think about it would be that if we suppress the tendency towards magnetic order, some other sort of instability will just leap out and become the new ordered state, because we expect to see order at the lowest temperatures. That's potentially okay, but I think a more accurate way to think about it would be that as we suppress the magnetic order, we make very profound changes to the properties of the excitations and the correlations that are present in the materials, and in such a way that the system is now primed to undergo another set of instabilities, unconventional superconductivity being one of them, but certainly not the only one. And so the next slide just sums up those observations in an abstract way, and simply draws a line under the differences, let's say, between a conventional phase transition, which happens when we lower the temperature and enter an ordered phase. I think we know a lot about that kind of phase transition, thanks to the work of Ken Wilson and to others. But on the other hand, if we find ourselves in an ordered phase at 0 temperature, and we apply a parameter like pressure, like field, like composition, and that has the effect of suppressing the magnetic order, we understand a lot less about how we go from ordered to disordered at 0 temperature. except that we end up, of course, in a disordered phase that has quantum character. And this is a regime, of course, that was famously studied or perhaps pioneered by Landau and his school in times past. Nowadays, much interest focuses on the vicinity of the zero temperature phase transition, and in particular, its non-zero temperature properties. And these were initially studied by John Hertz, by Andy Millis, by Sabir Sachdev, and by others. And they also will be this regime is also the focus of this talk. So in the next couple slides, I want to show you how different the properties of materials are near these quantum critical points. And I'll do that by looking at a few, let's call them benchmark materials. So this is ytterbium rhodium-2 silicon-2, a material that was heavily studied by Frank Steglich's group in Dresden. And what I've plotted here is the consequence of many resistance measurements that were carried out at different temperatures and at different fields. And what's plotted here is not the magnitude of the resistivity. What's plotted here is the temperature dependence of the resistivity. So at each temperature and field, the resistivity has a temperature dependence, which is a power law. And that power, N, can go from a 1, which looks orange in this plot, up to 2, which looks blue. So what you can see is at the lowest temperature, at both low field and high field, you see conventional Fermi liquid behavior in the ordered state and in the disordered state. But right where you're transitioning between those two states, you see something completely different, which is you see that the resistivity is linear with respect to temperature. It seems so simple, right? How could this be significant? Well, the answer is that we know that conventional metals, such as, let's say, lithium, have a resistance which is quadratic with respect to temperature. And we describe them, this is a manifestation, a sign of Fermi liquid behavior, which is what we expect in a conventional metal. In the case of ytterbium rhodium-2 silicon-2, the resistance is absolutely not that. It's linear with respect to temperature. So we know right away that this material is not a conventional metal, although it does conduct electricity. To give you some idea how robust that behavior is, here are some data, not as a function of field, but rather as a function of doping, that shows that this linear resistivity extends over 3 orders of magnitude in temperature. So there's some explaining to be done here. And our expectation is that the excitations that are behind that resistivity are themselves unconventional. And this turns out to be true. So I'm going to turn to another material, cerium copper-6 doped with gold. Cerium copper-6 is a relatively conventional metal, but when we dope with gold, we induce antiferromagnetism. And so if we sit right at this composition where magnetic order is just about to turn on at a quantum critical point, we can use neutron scattering measurements to study the properties of the excitations. So that neutron scattering intensity is plotted here at the right. And you might have said, well, you should plot it as a function of energy so we can see the energy dependence and do that measurement at different temperatures. And so that was done. But the data here are plotted not as a function of energy, but rather as a function of energy divided by temperature. It's really a very profound result, because think about it for a minute. Of all the excitations that you know and you learned about in school, every single one of them has a characteristic scale of some sort. Phonons have the Debye temperature. Electrons have the Fermi temperature. For materials that are near quantum critical points, the defining feature is that the excitations have no scale at all, other than temperature itself. And so again, that is a very strange kind of excitation. But it tells us that this is really a new kind of matter with inherently quantum mechanical properties. Okay, so we're going to go to the lab this afternoon, and we're going to actually, put our money where our mouth is. We're going to make a quantum spin liquid today. And so how would we go about doing this? And so one thing that you might think about would be that, we know that the magnetic order is the consequence of exchange interactions. And so according to the mean field, we have this expression where the exchange interaction is proportional to the ordering temperature. So one thing we could imagine doing is making a material where the moments are very far apart, so the exchange is very weak. But this doesn't turn out to be a very good approach, because you first have problems making materials where the moments are infinitely far apart so that TC could be zero. That could be a problem. And what's also true is that even if you could do that, you would find that the quantum critical behavior would also collapse to very low temperatures and very low energies with the ordering temperature itself, taking this approach. For that reason, a more conventional way, or a more successful way of finding quantum critical points would basically come down to finding ways to maximize quantum fluctuations in these materials. And if those fluctuations are sufficiently strong, order will be impossible. So one way that you can do that is by looking at materials that are intrinsically low dimensional from the electronic perspective, and so 1 or 2 dimensional. And the Merman-Wagner theorem tells us then that the long-range interactions are limited and magnetic order will be suppressed. Another possibility, of course, is that we could look at particular lattices, we call them geometrically frustrated lattices, where the interactions are very closely balanced and in fact can cancel each other out. And the fluctuations that you get in that kind of a system can be sufficiently strong to suppress order. And there are even systems where dimerization can also form these non-magnetic singlet states that compete with order. So I'm just going to make a note as I go by that there's an additional piece of this physics that I'll come to in a minute, which is different between metals and insulators. But for now, I can say that the essence of geometrical frustration, it can be basically understood by looking at the simplest example, which would be a triangle, where I'm going to put a moment on each of the vertices. And so if I insist that there's antiferromagnetic coupling between these moments, you can see there's no way for all the magnetic moments to be equally satisfied and they under this circumstance. And so the consequence that would be that in addition to this initial triangle, there are 5 other triangles that are completely equivalent. And so the system then will cycle among these different configurations. But of course, a system doesn't have like 6 triangles. I mean, a system has 10 to the 23rd triangles. And so you can see that there are many, many states that would be available to that system, some of them being ordered, but most of them, the vast majority of them, not being ordered. And so the system will cycle among these many different configurations, even at 0 temperature, by using quantum fluctuations. And it is this huge multiplicity, which is the characteristic of geometrically frustrated systems, which is why they're so good as quantum materials. And this slide is only to tell you that there are different variants on triangular lattices that have been explored. Some of them are more likely to be ordered than others, but largely we are still looking for a quantum spin liquid, which has strong magnetic character, but no order. So the last piece of physics that I want to lay on you is what I mentioned before, which is in our group, we're very interested in looking at metallic compounds. And so as I said, when I told you about the periodic chart, you have to take care to be certain that there is magnetism that is present when you want to study magnetism. And so this slide gives you a piece of why that's potentially so complex. So say I start up here at high temperature, and I have found a system in which we have localized D or F electrons, so localized magnetic moments. But they're in a metal, so there's some sort of exchange coupling between those moments and the extended states of the conduction electrons. So 2 things could happen as you lower the temperature. The first is that those electrons remain localized and they continue to bear their magnetic moment, and that all that would happen as you lower the temperature is that they could undergo magnetic order. And so we have localized electrons with magnetic order as our ground state if the exchange is weak. On the other hand, if we said that the exchange would be very strong, something quite different happens, which is that those D and F electrons become delocalized. And as a consequence of becoming delocalized and band-like, they are absorbed into the Fermi surface, which now becomes bigger than it was at high temperature. And so the consequence of that would be that the previously localized electrons become delocalized and non-magnetic, and that the Fermi surface expands. So as a function of this parameter, J prime, we see that there's a quantum critical point at zero temperature, which connects, on the one hand, magnetic order of localized electrons when that parameter is small, or the absence of magnetic order and delocalized electrons when that parameter is large. And so the difference between these two states is clearly the size of the Fermi surface. And so when you get close to this quantum critical point, you can expect that there are quantum fluctuations between those two configurations that can affect the properties of the material itself. And this is a piece of physics that is unique to metals. You will never see this in insulators because they have no Fermi surface. So summing up all those comments is our overall phase diagram. And we can see that there are two control parameters. One could be that exchange that I just told you about. It is pressure, its composition, its magnetic field. And this is a parameter that takes you from having well-localized magnetic moments prone to magnetic order and suppresses their magnetism and the magnetic order, yielding a non-magnetic Fermi liquid sort of state that has a large Fermi surface. On the other hand, even if you it's possible that if you have a strongly localized magnetic moment, that you can introduce quantum fluctuations in some way, and when they become sufficiently strong, magnetic order is no longer possible. This is the state that is of interest, the quantum spin liquid, where you still have magnetic moments, but you have no magnetic order. And so the name of our game is to try to find materials which are quite close to the quantum spin liquid so that we can drive that instability using some of the experimental tools that we have. So in the last part of my talk, I want to introduce you to a compound that we discovered that we think fills many of the requirements of a quantum spin liquid. And specifically, this material is called charmingly scandium-3, manganese-3, aluminum-7, silicon-5. We call it SMAS, S-M-A-S. And you can see that the magnetic moments are the manganese, and they lie on this lattice. It's this Star of David lattice. It's called the Kagame lattice. And you can see that triangles are a central feature of this lattice. It's a layered compound, as you can see. And we've grown some single crystals that are shown here from flux that we use to do the experiments. Now, nobody can tell you that there's a perfect material, of course. You're mostly theorists, so I have to point that out. But from the experimental perspective, these are very high quality compounds. The single crystal X-ray diffraction experiment tells us that we're at stoichiometry, and there are no departures from that stoichiometry or disorder between the sites. And this is ensured by the differences in the atom sizes in the compound. So it's a good material. It's also first in class. It's not the first metallic Kagame system that has been discovered. The table over here shows you a list of those compounds. However, many of them are not magnetic, and some of them are, let's say, too magnetic in that they order at high temperature. SMAS is a first-in-class material because I'll show you, we see no order down to 50 millikelvin, and we still have a substantial magnetic moment. And I'll give you more information about that in the next slides. So here's a plot of the resistivity of SMAS for two different samples. And you can see it's manifestly metallic in the sense that the resistance increases as you raise the temperature. Of course, the residual value is pretty high for a metal, and you can see that there's this upturn at the lowest temperature, but the sample independence tells us that this is an intrinsic property of the material related to the quantum fluctuations that are nearby. Of course, the most powerful way to get your feet wet with respect to the magnetism is to look at the temperature dependence of susceptibility, and that's plotted here at the right. And you can see that there's this 1/T behavior at high temperature above, say, 150 Kelvin. That's the Curie-Weiss behavior. And we've analyzed it, and the Curie constant is about 0.454 magnetons per manganese. Now, this is a value you will never get from the Hund's rules, and it tells you that the manganese states are not fully localized. Instead, they are hybridized with other states, largely the aluminum states in this system, and they form a band, but the band is somewhat narrow enough to sustain a spontaneous magnetic moment. But this seems to us to be a system that presumably has a large Fermi surface, although instabilities of the Fermi surface seem likely. Another point to make is that the Weiss constant that comes from the Curie-Weiss susceptibility is quite large. It's 175 Kelvin. It's negative, which means that the correlations, the mean field interactions are negative, are antiferromagnetic, but we don't see any sort of magnetic order in the system down to 50 millikelvin, despite the size of those interactions. And so that is a clear sign of frustration, where magnetic order doesn't occur, even though it could. So let's drill into the susceptibility a little bit, and that's plotted here. This is a log-log plot of the susceptibility, where we've measured it with fields in two directions. If it's in this direction, the field is perpendicular to those manganese planes, and in this direction, the field is in the manganese planes. And we can see that there's a power law divergence of the susceptibility when the field is perpendicular to the planes that extends down to quite low temperature. And the power law is sublinear. It's T to the minus 0.85. If we look with the field in the plane, we see a less critical behavior in the sense that the divergence is weaker and that it saturates at a higher temperature. The fact that the susceptibility doesn't fully diverge down to the lowest temperatures that we can measure is a sign to us that this is a material that actually doesn't order. It's close to magnetic ordering, but the correlations don't extend sufficiently far with respect to space, and they're not sufficiently long-lived to really seal the deal and become a true magnetically ordered system. So this is great. This is exactly what we would need. This broad peak is also seen in the specific heat, which is plotted over here. And again, indication that at best we get short-range interactions and we evade true magnetic order in this compound. So we wondered if we could use magnetic field as a tuning parameter for these compounds, as has been done in other quantum critical systems. And so we plot here the DC susceptibility, magnetization divided by field, as a function of temperature. And we do this in different fields. So at the lowest fields, you can see that there's a good critical divergence of the susceptibility cut off at the last moment. But that as we increase the magnetic field, we see that that divergence becomes weaker and weaker. And eventually, at the highest fields, the susceptibility becomes independent of temperature. That should be familiar to you because that is the behavior of a conventional metal, not a quantum critical system. So we can largely separate these data into data that are above, let's say, this black point, where we see a divergence of the susceptibility, and the data below the black point, where we see increasingly a temperature-independent susceptibility. And so those data are organized here on the right into at low field and a full range of temperatures, the true quantum critical behavior of the system. And then if we get to high fields, we see a conventional metallic behavior, the Fermi liquid behavior, where essentially the quantum critical behavior has been suppressed by field. And so that led us to believe, of course, like, which is more important, the temperature or the field? That's kind of a good question because, our fallback position is always to say materials like this could be excellent for quantum sensors because they work at zero temperature and could potentially detect magnetic fields. And so the answer, as we found, was that neither temperature nor field by themselves is the control parameter. It's a combination of temperature and field that controls the magnetization. So the evidence for that bold claim is shown here. I've plotted the derivative of the magnetization with respect to field. That's the susceptibility. and I multiplied it by a power of t to the 0.85, which is the same power that you saw in the susceptibility, the zero field susceptibility. And I plot this not as a function of field, not as a function of temperature, but a field to the 0.85 divided by temperature. And what you see is that for a wide range of temperatures and fields, that the magnetization collapses onto this universal curve. And it says, it doesn't matter what field you choose, as long as you choose the right temperature to go with it. And if you do that, we can always predict what the magnetization is. And so that's a second piece of information, which is the magnetic field is a critical parameter in this system, and that both field and temperature control the properties of this material. So by conclusion, I want to return to our phase diagram where we have quantum fluctuations of unknown strength and moment hybridization, the delocalization of moments, also of unknown strength, and where would we place our material. And my proposal is that we would place SMAS essentially here. We know that it is a large Fermi surface system because we otherwise could not explain how small the manganese moment is, but the manganese moment is not zero. And so that tells us that we must be relatively close to this critical line, which is where the Fermi surface, the extended Fermi surface, the large Fermi surface collapses. So somewhere close to this line. We also know that this material forms on a geometrically frustrated lattice. We have to believe that that plays some role in introducing quantum fluctuations. And so we also know that we have to be somewhere up the vertical axis. And so that is how we place this material. You can see that there is this blurry line here. And this is meant to represent a crossover between a highly correlated Fermi liquid state and the true quantum spin liquid. And in our future work, our intention would be to modify this compound so that we could drive it continuously across this crossover into the quantum spin liquid. We feel we're close enough to be able to do that with the tools that we have at hand. And just as sort of a last self-indulgent point, I'd like to also say that one of the reasons, why people are interested in finding quantum spin liquids really dates back to a proposal by Phil Anderson in the 1970s, which was that these frustrated systems would be good sources for unconventional superconductivity, provided that they could become, that they were metallic. So from the history of cuprates, that there have been decades of efforts to try to dope insulating compounds. And this is why we feel that it could be advantageous to pursue materials such as this one, because it's intrinsically metallic. And so that part of the job has already been done for us. All we need to do, apparently, is to control the magnetism. So of course we don't, if we had a Kagame superconductor with magnetism, I would definitely have talked about that. But just to give you an idea about what our eventual intentions would be. So thanks very much for listening, and I would be happy to entertain any questions that you might have.
Many thanks for a great talk, Megan. It was very pedagogical, very clear. And I don't see questions on the chat, but I have several questions. The material you shown, this very interesting one, then have you or others look at what happens when you do, like in niobium diselenide, people do like they cleave, essentially they peel them off, essentially. So the idea is to have the system more 2D by peeling off. Some people use Scotch tape, some people use different techniques. The idea is to remove layers and then eventually you could have the system which is thinner and thinner and thinner and thinner. And then what happens if you have one layer might be very difficult, but it has 2 layer by layer. So therefore you could see the 1 layer pure layer because then you don't have the 3D component, or 2D like bilayer graphene. So it will open like a new something like this twisted kind of possibilities of lattice depending how you superimpose them. So I was thinking in terms of more like niobium diselenide or one of these materials you can peel off.
Yeah, indeed, you know, at our QMI, some of my colleagues, Keizo and Marcel Franz, and Zilian, have experimental programs in this area. They're not looking at this compound, at least not yet, but I'm familiar with this kind of approach. I can only say, you know, we are really at the front end of the materials discovery, program, and that, you know, my colleagues are, for instance, looking at graphene, which is a, you know, well understood and highly idealized kind of compound. You know, the problem with being us is that, you know, it's a long time until you can convince people that the material is ideal enough. And indeed, it may not be ideal enough, you know, after we've done, you know, more work on it. So I think that that's a really important and interesting way to go. And, you know, ultimately for quantum sorts of applications, I think that you're always going to want to integrate the materials into devices. And so, you know, that's, I think that's the long-term dream, but not the short-term one.
I don't know if it is easy or not difficult, like to take some sort of like a machinery, like a laser cutter or knife, to be able to do like thinner and thinner, and then you can see the scaling, no, as a function of the thickness. But this might be difficult to do because, I mean, for magnetic materials, people don't do Scotch tape. They might be able to do like cleaving. Now, the other question is, when you show resistivity versus temperature, as you were pointing out, I mean, it's metallic, but then eventually there is like a saturates, and then there was slightly going up between 50 Kelvin and below. Is this something related to like a localized magnetic impurities, condo-like kind of like a...
So I tend to agree with you completely. And so the point that I made was that upturn is related to critical fluctuations, right? And we know that because the temperature and field dependence would have scaling properties that are similar to the magnetization. And so in this material, we believe that the fluctuations are in part just straight up magnetic fluctuations like you'd have near a magnetic phase transition. But also, because of the reduced moment, we feel that there are critical fluctuations of the type, which is you have a large Fermi surface that contains the d electrons from the manganese, and then you have a smaller Fermi surface that does not. And that at the quantum critical point, they're degenerate. And so if you're close to the quantum critical point, you can expect that there would be fluctuations even at zero temperature between those two configurations. So it's more complex than a simple magnetic ordering. We understand the Kondo effect, you know, which is sort of the classic way to understand the stabilization of a moment as being a special case of that, where you form a singlet, or you can form a triplet between the conduction electrons and the local moments. And so, you know, it's an impurity problem, so there's not a Fermi surface per se, but it's a very similar kind of phenomenon, I would say. So you're exactly right that that's how we would interpret the upturn at low temperature. And it leads you to a very complicated situation, of course, because we were taught in school that the resistance can only be infinite or zero at zero temperature, right? And so how can you understand a system where there's something else? So yeah, just leave that with you for fun.
I was thinking the following, no? As you correctly pointed out, you can go to the critical point by going lower dimensionally. So if you have your new great material, then I was thinking, peeling off, I was thinking like 2D approach, but what about if it is not just 2D and 1D, namely making it more and more one-dimensional? I mean, some people use, you know, in materials are like laser cuts, or I don't know how people will cut it nicely. But if you have a 1D, then you could have a very nice candidate for quantum spin liquid on 1D. And then if you could have the 2D, ideally, I mean, this is like a thing with as a function of thickness. So you go 3D bulk, and then you make it thinner, thinner, thinner. And then with the stripe, you become the stripe narrower, narrower, narrower. I know this is easy to see, to do, and difficult to make in the lab. If you could do it, you could see the crossover from 3D to 2D and from 2D to 1D, including the ladder cases. And then I think this would be fantastic, because then the people who do, let's say, numerical simulations can simulate nicely 1D, can do the ladders, can do, even 2D. By the time they get to 3D, it might be more difficult. But then this is something that I think could be a nice possibility, which I don't know, like to explore. I don't know, like thinking loud here.
So we're not so much into shaping materials, I would say, but we have a separate project in our group that we've been working on for some years, which is to find 1D systems. And the huge advantage of 1D systems is that there is a smoking gun, and that is whether you see spin-ons or not. So we have two systems that we found that are metallic and are definitively 1D. So one of them is definitely a small Fermi surface system based on F electrons. And the more recent one that we've been studying is a D electron system, where it's true that the conduction electrons themselves are one-dimensional, and you have a one-dimensional magnetic subsystem embedded in that 1D metal. In any case, that would be another talk, but we are using the same sorts of approach, which is basically mining the International Crystal Structure Database, for particular lattices that we think would support low dimensions, or in this case, the Kagame lattice.
Okay, great. So therefore, let me just click here to see if there are questions from Kigali here. Okay, there is a Dev Dut from Kigali. How quantum liquid is different from Bose-Einstein condensation state of liquid, if possible?
Oh, yeah.
I think they're very different.
I think that the statistics will be rather different. I think we're guided by the existing theory to in magnetic systems to basically think that they are more fermionic kinds of systems, and maybe the evidence that we have for that would be neutron scattering experiments will often support that conclusion. And certainly in the 1D systems that I was just talking about, I think we know for a fact what the excitations are, and that is is backed up by an exact theoretical result. So we are not in the Bose-Einstein condensation situation, but we would love to be, but it would be by accident, I think, if that ever would happen.
Great. There's another question by Debasis Wayne. What is the difference between quantum spin liquid system and quantum spin glass system? And I mean, my quick answer will be one of them is frozen, the other one is moving around. So it's like a liquid versus glass. So that would be my quick answer, but please go ahead.
Well, you must be listening in on our group meeting lately. So it's difficult, right? And so when we look at like a low dimensional system, right? And what we find is that, let's say at a certain energy scale, what you'll see are the spin-ons, which are the characteristic excitations in 1D. But what you'll also see as you go to the lowest energy scales is a very broad spectrum of fluctuations over many orders of magnitude in time scale. And so if you look at the longest time scales that are accessible using something like μSR, what you'll find is something that looks canonically spin glass-like, in the sense that you have some kind of a stretched power law spectrum at low temperatures. But you keep going and you go to AC susceptibility that you can measure in your lab, which is super slow. And you see that those excitations just keep on going, down to the longest timescales that you have. So I think that functionally speaking, you can't really identify, I mean, you can't see something that's frozen. All you can see are fluctuations that become slower and slower and slower. And so I believe you can't differentiate between a quantum spin liquid, which has a broad spectrum of excitations, and a canonical spin glass. But in both cases, whether or not you have a quantum spin glass or a quantum spin liquid, I think that that you have excitations that are present at arbitrarily low energies. That would be our definition. But in a real system, the time scales probably don't go to infinity. But thanks for the question.
Okay, great. Well, thank you very, very much. And then let's thank the speaker for a great talk again. And
Thank you
thanks
very
for
much
having you here.